Okay, good. Thanks.
Good?
Yeah, perfect. Okay, so how do I... Okay, great.
So let's pass to the next talk. Bogdan will tell us about massless modes and the AdS3 CFT2 Quantum Spectral Curve.
Okay, thank you. And thank you for the invitation. It's an honor to speak to famous physicists like Nadav at famous institutions, you know, like this institution. So it's a great pleasure. But I'm just trying to continue the theme of yesterday's format. So I'm going to... Oh, hold on. Give me a chance. So this is based on some work that Simon Ekhammar, Kolja, and I did in this paper, and also in ongoing work that the three of us, together with Charles Thull, who is my postdoc, he's sitting in the front row here, have been doing. And I just want to emphasize that besides this old person and this slightly younger but still old person, there are two really excellent younger people who've done a lot of brilliant work. And I want to stress that you should be really thinking about them when you're thinking about this talk. And of course, my old but young collaborator. So I guess we had a very nice talk by Davide, who introduced a bunch of these things. But coming from a string theory background, I just want to frame this in a slightly bigger picture, because I feel sometimes some of the string theory detail gets a little bit lost. So actually, AdS3 S³ T⁴, what we mean by that is a near horizon limit in the Maldacena sense of a bunch of D1s, D5s, F1s, and NS5s, right? So the D5s and NS5s in general are parallel, and the D1s and F1s are parallel and sitting inside the 5 branes. And so really, there's a lot of different charges that we can pick, right? So it's not like D3 branes, AdS5, where we pick one integer. Here, we're really picking 4 integers. And even this is a slight oversimplification because there are T-dual pictures, but I'm not going to get into that. So if you compactified type 2 string theory just on T4 in flat space, you would have 25 moduli on this T4 that you could change, and it would, they're all moduli, so you could change them freely. But because you've got a curved geometry, 5 of those moduli get removed. Okay? So instead of just having what we're used to in AdS5, having this lambda parameter that we can tune, here there are 20 parameters that we can tune, and these 20 parameters are different depending on which charges you pick. Okay? So what we tend to think of in the integrable setting is that we have 2 parameters, one which controls the number of Navier-Schwarz 5 branes, and the second parameter which controls the number of D5 branes. And the number of D1s and fundamental strings has something to do with the volume of T4, depending on exactly which charges you choose. But the volume of T4 never features in our discussions to date. And so somehow it's only really these 2 integers, the number of D5s and Navier-Schwarz 5 branes, that are important. Okay. Yeah, so feel free to interrupt me, obviously, if you have questions or saying something that's not clear. And this case, as we heard in the previous talk, where K is non-zero but H is 0, should give this very beautiful Maldacena-Auguri WZW model whose spectrum is completely known. On the other hand, going away from this point in the Maldacena-Auguri language, in the RNS formalism, is essentially impossible or very, very challenging, right? You can turn on a little bit of Ramon-Ramon flux, but turning on a lot of it is, you have to calculate order by order, insert more and more vertex operators for this H deformation, and so it becomes very hard. On the other hand, the k equals 0 case, which is what I'm going to talk about in most of this talk, is, well, not really connected to this Maldacena-Auguri point, and it's only integrable methods that you can use to calculate anything. Okay, so this slide I'm going to skip, and you can ask me about it afterwards. It's about the CFT2 side of the correspondence, and all of this is to say that we know extremely little about it. So ask me later. So now I'm going to get into sort of slightly more familiar territory. What I want to do is I just want to introduce these ideas that probably a lot of you know very well, but just in the context of AdS3. So you take, let's first talk about the S matrix of this background. So you take a gauge-fixed Green-Schwarz action. This is my attempt at schematically drawing a magnon scattering with another magnon, and notice that the world sheet is infinitely long. And when you do the scattering, you can figure out that there's an exact dispersion relation that in the mixed flux case was first proposed by these guys, and then we generalized by us to massless modes. But the S matrix that you obtain, the two-body S matrix that you obtain in this process fixed by symmetries, satisfies the Young-Baxter equation and can be most nicely written in terms of the Zhukovsky variables. So I'm very happy that Davide introduced these variables in the last lecture, so I can go, in the last talk rather, so I can go a little bit faster. And for the most part of my talk, I'm going to be setting k equal to 0. Remember, I'm going to be in the pure Ramon-Ramon case. So there isn't really a distinction between left and right moving particles. But what's new compared to AdS5 is that there are these massless modes. So in AdS5, we not only have k equal to 0, but we always have m equal to 1. But here we can also have mass equal to 0. And OK, I don't really want you to absorb all the information on this of these terrible Bethe equations, or huge Bethe equations or beautiful Bethe equations, depending on where you are on them. But these Bethe equations have got a bunch of roots, some of which are auxiliary roots, some of which are momentum-carrying massive roots, but there are also these massless roots, right? So from n equals 4 or AdS5, you'd be familiar with these roots. This would be like a subset of all the roots that you have in AdS5, but there are these additional massless roots. And the Bethe equations, the only thing I really want you to take from this long expression is that they have a bunch of rational terms in terms of the Zhukovsky variables, but they also have these dressing phases, very much like what was introduced in the last talk. So here is a dressing phase for the scattering of two identical massive particles. Here is a scattering of a left massive particle with a right massive particle. And here is a dressing phase, for example, of a massive and massless particle. So the circle, as opposed to bullet, is meant to be massless, as opposed to massive. OK. And similarly, in the massless Bethe equation, there is a dressing phase just involving the massless particles, and one involving the massless and massive ones. Okay, so this form of the equations is fixed by this symmetry argument, and the dressing phases satisfy certain crossing equations that have been known for a while. But what happens is, if you try solving this Bethe Ansatz, you're really getting the spectrum of the theory as the world sheet is very large, as L goes to infinity. And in AdS5 and AdS4, this is not a problem because, or at least it's a sort of very valid approximation, because wrapping effects, so going around the world sheet, are suppressed exponentially with the mass. In AdS3, we have massless states, and the mass can be 0, so this exponential suppression goes away. And so that was a point of view that Aniceto and Abbott emphasized. I should have included their papers here that emphasizes some potential challenge to the asymptotic Bethe Ansatz in AdS3. So we were able to, back in the day with Alessandro Torielli and Diego Bombardelli, we were able to come up with a massless sector TBA, which seemed to overcome these problems. But actually, looking more closely, it turns out it's the interaction between the massive and the massless states that is yet another challenge on top of that. So I think the more modern methods of the quantum spectral curve, of the TBA, allow you a way of incorporating these wrapping effects, these massless wrapping effects, and not, you know, place the asymptotic Bethe Ansatz in a much sort of firmer footing and tell you about in what limit it is valid. And what seems to be quite nice about the quantum spectral curve is that the internal kind of bootstrapping consistency of it places even stronger restrictions, as I'll try to show you in a bit. It places even stronger restrictions on these dressing factors. And so there are some little subtleties that we were able to fix by looking at the self-consistency of the quantum spectral curve. Okay, so I guess maybe 2 years ago now, these two papers of Andrea Cavaglia, Collia, Alessandro Torielli, and I, and a paper by Simon and Dima came out at the same time, in which we looked at the Q system of PSU112², which is the symmetry of these AdS3 backgrounds. And the Q operators should be roughly familiar to you if you're familiar with the n=4 theory. There's just a bit fewer of them. And amongst them are sort of some preferred operators, which are called QK, and some other ones which are called PA, and K and A both run over 1 and 2. They're in the fundamentals of the non-compact and compact SU2s. And there are these QQ relations. So this is for one copy of PSU112, and then there's a second copy. So let's say this is the left one, and then there's a right one where you put dots everywhere. So for example, amongst these relations, here is a Q, here is a P, there is a particular relation between the Q's and the P's and the Q's A/K's. And there's lots of these relations, and the consistency of these relations is what's important to be able to construct the quantum spectral curve explicitly, and these plus minuses are, of course, the famous shifts in the Zhukovsky variables by plus or minus 1. Okay. But that's not everything. You still have to tell me what is the analytic structure, right? So these Q functions have a certain analytic structure, and it's always assumed in these games that the P's have a single shortcut that goes between minus 2h and 2h, where h is the coupling constant, and that what this implies from the QQ relations is that the Q's themselves have got either cuts, an infinite tower of cuts below the real line, that's these guys, or an infinite set of cuts above the real line. And so there are these two solutions, because the QQ relations are essentially, that part of the QQ relations is a second order difference equation, so you get two linearly independent solutions. So what should you do with them? Well, actually, in the Gong show, we heard something similar already. There's a gluing condition, right? Which tells you that the Q's with cuts in the lower half plane are related, the left Q's are related to the right Q's with cuts in the upper half plane through this constant matrix G if you go around and through the cut, through this cut of the P function. So this is gamma, and this is gamma bar, what we're going to call like this. And one is, of course, the inverse of the other. And the matrix G, the gluing matrix, turns out that you can take to be in this form, off diagonal, with some constant alpha. Okay. And once you have these relations, it's often also very useful, just like in the AdS₃ case, to introduce the Q omega and the P mu systems, where essentially you relate what happens to Q under the deformation gamma to Q dot guy through this function omega. And so these gluing conditions, together with the QQ relations, allow you to determine that there's some operator omega, which takes this form here. Similarly, there is a P mu system, and P under now gamma bar, so remember gamma bar is going in the opposite direction to gamma, is related to P dot operator with this with these mu's, and these mu's, again, through the gluing conditions here and the Q relations here, if you work a bit, you can find out that the mu's look like this. There's a question? No, we good? Okay, so if you want, that's kind of the construction of the quantum spectral curve, but one really nice feature is that it's possible to take a limit of this, of these operators, where you declare that some components are large, and as a result of the QQ relations, others are small, and you study the quantum spectral curve in this limit. And in the limit, you can recover the Bethe Ansatz equations, the ABA equations. So in these papers, it was proposed that you take omega 1, 2 dot and 1.2 large based on experience with n equals 4 quantum spectral curve. And as I'll sort of review shortly, if you do that and kind of apply the AdS₃ methods, you will recover the massive Bethe equations. So just the subsector involving only the massive roots. But more recently, it's been proposed that there are some the massless modes. So that was following these papers. There was this puzzle, right? What happens to the massless modes? The massless Bethe equations should somehow be encoded. And what we did more recently with Simon and Kolja is we proposed that there are zeros of the mu functions, which will correspond to the massless modes. And this was very much motivated by earlier work by Simon, Kolja, and Nicola Preti, who looked at as a kind of more complicated subsector of n equals 4 theory, where you take non-integer spins. So this is in a much more sort of complicated setting. And they found that there were massless modes and zeros of these functions that appear there too. But here, these zero modes already appear in just the perturbative closed string spectrum, rather than in some more complicated analytic continuation. Okay, so like I said, we specify that these guys are going to be large, and then we just apply the QQ relations. Okay, and this is, I'm obviously summarizing here a lot of computational detail, but these QQ relations, together with saying that some things are large, really restrict what the P's and Q's can look like. And some part of the ones that remain, so these are the ones that remain. And some part of it is kind of, let's say, simple looking, so it's kind of rational looking. So you see you have these B's and these R's, they're all rational functions. And also, you get these new massless roots appearing here, and they also appear essentially rationally, okay, with a square root, but essentially rationally in the definition of the P's and Q's. But in addition, there are some factors which are undetermined, which will contain the dressing phases. Okay? And it's this part that's kind of most interesting, because when you plug those in, the gluing condition that I told you about imposes what look like discontinuity equations for these different dressing factors. Okay, so you can obviously, I can't show you all the details of all these expressions, but you get some discontinuity equations for each one of these dressing for each one of these, well, they're not really dressing factors, these scalar factors. They're sort of like half of a dressing phase. And these discontinuity equations are very explicit, and so it's possible just to solve them. You know that there is some cut. When you cross the discontinuity, you've got to get a bunch of stuff like this. And don't worry about the fact that I've got proportionality constants here. We actually know how to solve this with an equal sign too. I'm just being quicker here, suppressing some technical details. Okay, so let's take one example. Let's look at this particular scalar factor, which, as you can see, has something to do with massless modes. And let's try to solve this equation. And it turns out that the solution, well, for those of you that are now familiar with quantum spectral curve technology, these factors typically come as a product over all the, in this case, massless roots. And each one of these row circles takes this form. Thanks. So there's some scalar factor, which is some kind of rational factor, which is not very important. There is something that I've called theta relativistic, which, see here I have x and y, and here I have gamma 1, 2. And gamma 1, 2 are these beautiful variables that Andrea Fontanella and Alessandro Torielli introduced. And what's nice is that this factor here, it takes a difference form. And the explicit expression for this, somewhat surprisingly, is, well, up to this sort of minus sign if you want, is exactly the same as the dressing factor of the Zamolodchikovs in Sine-Gordon soliton anti-soliton S matrix, like the very first integrable paper on this subject. So you can see that basically this row wants to be this Zamolodchikov dressing factor. But there's some slightly annoying constant phase that seems to come up. Okay, and I'm going to talk a little bit more about that now. Okay, so how do we get the massive Bethe equations? Well, this is a kind of well-trodden path by now, similarly to AdS₃. You take certain combinations of the Q functions, you evaluate them at the zeros of certain functions, and plug in these large volume limit expressions. Whoops, I'm going the wrong way, aren't I? So you plug in these sorts of expressions and similar ones for the Q slashes, and you recover the Bethe equations that I showed you at the beginning. And you recover them only as long as you identify these scalar factors from the quantum spectral curve with the dressing factors of the S matrix in this way. So you have to make these free identifications for massive left-left, massive left-right, and mixed mass scalar factors. And you see here there are already 6 equations. So actually there's a lot of consistency condition that comes in. Each one of these equations looks slightly different. You only get 3 choices. You got to match to 6 equations. So it's non-trivial that this works out. What about the massless Bethe equations? So this was the kind of new contribution of the more recent paper. If you look at this combination of the P functions now, and you evaluate them just above and just below the massless cut, then you reproduce, so again, I'm not showing it, but you reproduce the massless Bethe equation up to some strange phase, which I'm going to keep drawing now in light blue, and this strange constant phase I think deserves to be understood a little bit better. It sort of has the feeling of like a twisting just of the massless sector, something like that. And again, the matching works as long as you identify the S matrix dressing factor in this way, the massless one, and the massive one in this way. Okay, so that's nice. But what's even nicer is that if you calculate in the quantum spectral curve, we can understand crossing as a combination of doing this gamma bar contour and, as a combination of a gamma bar contour shifted one down and one up. So I think this is this kind of familiar to everyone who's looked at crossing in AdS₃. The crossing transformation involves crossing both x plus and x minus. And in the massless case, as was shown by Sergey and Alessandro, crossing in fact is gamma that I introduced earlier rather than gamma bar. Okay? And so since we know the solutions, right, and since we know what discontinuity equations these guys have to satisfy from the gluing conditions of the quantum spectral curve, we can plug them in to our expressions for, for example, here, the dressing factor is this particular combination of the quantum spectral curve scalar factors. So you can plug in and work out what are the crossing equations for all these guys, for all the dressing factors made up of these combinations of the scalar factors in the quantum spectral curve. And at first we were very excited. It was really nice because all the crossing equations come out exactly the same as in the S matrix. So that was a nice consistency check. And then if you look at the explicit solutions, so not just the crossing equations, if you look at the explicit solutions, they lead to the same dressing factors that we heard about earlier today, but just with k equal to 0, for the massive and mixed mass cases. But there was a funny disagreement between the quantum spectral curve massless dressing factor and the one that seemed to come out from the S matrix. So if you remember, I showed you one quantum spectral curve's scalar factor, which was related to the Zamolodchik of S matrix. There's also this other factor from the massless BES phase. So this kind of looks nice, but then there's a weird factor of -i, which is related to this e to the minus 3 pi I over 4 that I showed you. And this disagreed, and so this expression disagreed with the S matrix result of, I guess, Alessandro and Sergey, where they, instead of this -i, they had a factor like this. Now, what's also funny is that if you take this scalar factor, sorry, this dressing factor, and you ask, is it unitary? It doesn't look unitary. So then you've got this tension, right? This scalar factor solves what we think is the right crossing equation, but doesn't look unitary. Weird, right? Maybe, instead, what we should do is, we should change this guy by a factor of I, so that we have unitarity, but then the price we end up paying is that it'll solve a different crossing equation. It'll solve a crossing equation with an extra minus sign on the right-hand side. So from the point of view of the quantum spectral curve, that's not a problem, right? Unitarity seems much more important than some arbitrary crossing equation. And we are allowed to do this change by I. It doesn't mess up the identification with the Bethe Ansatz equations, because there is this funny blue constant phase floating around, and that phase allows you to reabsorb these factors of I. So the conclusion that we were drawn to, oh, sorry, let me just say why, maybe, do I have like 3 minutes? 2.5, wow, strict. Just 1 sec. So I guess that's one possibility, right? That you redefine by I, but then maybe we should match to Alessandro and Sergey's answer here. How could we do that? Well, one way we could do that is we could take our solution of the discontinuity equation and multiply it by some extra factor so that it gives you the right, so that it reproduces this term in the dressing factor when you put everything together. But this actually introduces a much bigger problem, because what happens is the dressing factor for massive massless scattering will then change dramatically by a term like that includes this, so it's some non-trivial function. But on the other hand, the dressing factor for massless massive scattering remains unchanged. And these two guys are related by unitarity. So now you really mess up unitarity badly if you introduce this extra factor, right? So this felt to us to be not quite the right solution, and so we preferred to instead put a factor of I here. And I think recently, correct me if I'm wrong, you guys have kind of looked at massless crossing again, and in the S-matrix formalism, and it looks like, am I right in thinking that maybe there is an extra minus sign hiding there somewhere?
Yes.
Okay, so.
Well, the original reason is because we couldn't generalize with A of gamma premix plus. That's why we approached different methods.
Okay.
I will ask you.
Yeah, so maybe we discuss a bit more, but what I'm trying to say is that there seems to be a nice thing happening now fitting. So from the quantum spectral curve, it's sort of much nicer not to have this factor of minus I, because then really the massless dressing phase is really the Zamolodchikov of one, and that seems to fit with the latest analysis. Okay, so let me finish on some work that, that's perfect, that Charles, who joined our collaboration, and Simon and Kolja and I have been doing, but really a lot of heavy programming by the impressive junior collaborators here, so I want to just emphasize how challenging, these slides are going to make this look simple, but it's unbelievably impressive what those guys have been able to do. And so we tried to find some new solutions to the quantum spectral curve, generalizing these massive solutions here, but this is very hard because of the log cuts that are present. It turns out that if you consider as kind of symmetrical sector where the left and right P's and Q's are equal to each other, which in particular implies this for the spin and off-diagonal component of angular momentum, you can find solutions, exact solutions to the quantum spectral curve, which have just massless excitations. So this is the angular momentum, and we will be setting K0 to 2, and we will be setting L to 2 or 4, and then you will get the anomalous dimensions. And I just want to caution you, everything on this slide is still work in progress, so the numbers may change, but I think we're quite confident of the general structure. So here is the L equals 2 anomalous dimensions in the dots, the numerics, and I guess the analytics, right? And here is the, this is the curve I should have been pointing. The solids is the numerics and analytics at weak to strong coupling. And for L equals 4, this is the curve. And as you can see, asymptotically, they tend to these very nice Regge trajectories that we've been hearing about in this conference. And it's also possible to find the analytical solution in the case of L equal to 2, so these very short operators just with 2 massless excitations. And okay, again, caution, but the general structure seems to be a one-loop correction, and then I guess not the next order, but the 2 orders after that correction, and something at 6th order. Okay, so let me conclude. The AdS3 CFT2 quantum spectral curve in the Ramon case, well, it passes all these nice consistency checks and in matching to the ABA, and in particular, it seems that the original proposals were already kind of good enough. They knew about the massless modes, even though we didn't know about them back then. And we seem to get some nice sort of tying up loose ends results about the crossing and dressing factors, and in particular, it seems like there shouldn't be anything here. That seems nicer, and the old Zamolodchikov dressing phase shows up. And I hope maybe in the near future we will have some more concrete results about the numerics. Okay, so let me stop here. Thank you. Sorry, I overran a bit.
Questions? Joe?
Sorry, in your last slide, what is G?
I guess it's H.
So it's A. It's
Yeah, it's H. So yeah.
And there is no field theory to check it, yes?
There is no field theory to check it. Yeah. So, sorry, what?
That's what I'm asking. There's no field theory to check.
Yeah. So, but what do you want me to do, right? Ask Juan. So there are some words, right?
So in a sense, it's alpha prime. It's square root of alpha prime.
Yeah. Well, but that's at strong coupling. No. So, right, that's at strong. No. So this is done in the quantum spectral curve at small values of H. What's the dual field theory? I don't know. Well, I can. Here's my slide, words. Who knows? Is the summary we can, I mean, we've talked about this before, right? It's something to do with a deformation of symmetric T⁴. There will be some point in the moduli space of that thing which should match. How you calculate at that point, I don't know. There is a nice Higgs branch story which might be related to this that I talked about 10 years ago at this conference in London. But it's, yeah.
I also have a question about this sign, which is not very clear to me. The reason why we revisit the crossing equation because the point is that this A of gamma factor in the mixed flux, we couldn't generalize in such a way that satisfy all the properties. In particular, there is an SU2 or symmetry between the two massless modes.
Yeah.
And we didn't manage. So we revisited crossing, and our approach was more Lasciota, Copetti, and Ekhammar. In this case, what I don't understand is that you have some quantum spectral curve. You derive a crossing equation from a quantum spectral curve with a, do you have some freedom in choosing the sign from your QSC or
No.
So in principle, you should have this I factor or
So, yeah, I mean,
it's not completely clear to me this.
so because we have, well, look, in the massless case,
maybe we can.
you want to, sorry.
I mean, we don't derive S-metric, and we
Yeah.
derive the equations for the spectrum, we derive Bethe Ansatz, and then it's up to you to identify what is dressing phase, what is not. That's just a name, right? Doesn't make sense.
And the gluing condition has no freedom in it. There isn't like some hidden minus sign.
Then it's just a freedom of notation, right? So you can, sigma, 0, 0, this combination or that combination. And then, of course, unitarity and crossing changes each time you change notations. That's it. But there is no freedom in the Bethe Ansatz you get. Just a notation. Well, crossing equation is always is uniquely fixed. What is not fixed is left-hand side because you can change notation of what you call the dressing phase. Because obviously you can reabsorb different factors and Bethe Ansatz and say, maybe that's dressing phase or that, right? The same thing as you doing, right? In different papers you call different factors absorbed into sigma or not. That's the only freedom because there is no objective way of defining what crossing phase is. This is a quite ambiguous notion itself.
I guess
Normally in massless mode, you have different branches of kinematics, left, right, depends on. Is an assumption what you verify that there is a single dressing factor to the massless? Is an starting assumption or is something you can derive? Because from the bootstrap, as matrix bootstraps, people assume that there are different, there is a single analytic function for the dressing factor, which is the same for all chiralities. But
I'm not sure that there are genuinely different massless. I think this a little bit like to do with, I'm happier to go to the 2π limit rather than to the 0 limit, and so then it's, there are those two things are connected, right? As I analytically continue. Yeah.
So on the last slide, the analytic data is at weak or strong coupling because it's like in the right side of the
sorry, it's at both. So there is numerics at weak coupling, and then there is an extrapolation like this to stronger coupling.
Okay, and an analytic prediction at weak coupling.
And in this particular case, there is an analytic. Yeah, I think for L equals 4, it's hard. It seems to get an analytic expression.
And another fast question. So is there any confirmation of the predictions of quantum spectral curve, any matching with the actual string theory data, with classical solution or with anything?
These are, so we were looking really at the massless guys, so those are very hard to understand.
Okay, in this case, right, but in general for AdS3, I mean, we don't know how to compare with field theory. Can we compare something?
Did you guys compare in your earlier work on the massive case? I think the trouble seems to be these one-loop corrections, right? That they are quite problematic. They're the ones that you know well about.
Hi, Bogdan.
Hey.
So if you set h to 0 in your very impressive Bethe equations, asymptotic ones, do you get something that looks like a spin chain or a quantum field theory?
I mean, at weak coupling, you are asking. So not really to 0, you mean the first order guy?
Well, in n=4, you can set...
Yeah, okay, in the same sense that you mean, yeah. So for the massive ones, you get these spin chains that are, well, they are essentially a projection down of the n=4 spin chain, right? And for the massless ones, I don't think there is going to be a spin chain as such. I think our conclusion, Ale, was that it's like some kind of field theory, and it would be nice to understand this field theory a bit better, and it was starting to look like a n=2 sine Gordon, but not quite. And these dressing factors that I was showing you, these Zamolodchikov dressing factors, they kind of have that feel. So, if I'm just going to start dreaming now, as opposed to, thinking rationally, I would like to have a spin chain that interacts with like a sine Gordon field theory somehow, and that's what's at weak coupling.
That short comment. So in n=4, you can also get non-trivial
In chains like that at 0 coupling, but if you start from non-local operators like BFKL, you get exactly similar massless modes, and those dressing phases are quite similar. So it looks like it's a field theory, but operators being kind of a bit non-local. Maybe you can model it this way.
Thank you.